The talk I'm going to give has the provocative title, Neural Networks Are for Typecasting. So the TLDR here is that the embeddings of a neural network obtained by training on a difficult task are often more useful than the outputs. And the main contribution here is that I like to think about these embeddings actually as types, that they're sort of analogous to like 32-bit floats or 8-bit integers. And the only difference is that they are learned rather than designed. And so the goal here is basically to present an intuition for embeddings in neural networks that are that's maybe closer to the intuition that people who have a programming and CS background bring, rather than sort of like a math and physics background, which is where the idea of embeddings comes from. Or if you're not one for nuance, if I wanted to put this talk out there on the internet to get clout and put out my hot takes, the purpose of neural networks is just glorified typecasting. So to be clear, when I say types, like a type is just a collection of data values with a name. So integers. This is a collection of bit strings that have a particular name. Dictionaries, phone numbers, these are the same thing. And that name basically just describes how those values are to be interpreted. Maybe it suggests, okay, that what do you do with a phone number? Well, maybe you pull off the area code, or maybe you send it to a phone app. Whereas an integer, even though it might have the same underlying bit representation, you would do something very different with it. And it's important to note that though types are completely unnecessary for computation, you can do anything that you could do with types without them. They're extremely useful for thinking about computation. And so when we want to organize our thoughts around our computation, when we want to communicate what's important, what's not important in our programs, or when we want to obtain a mathematical understanding of what is and is not possible with different kinds of computing, adding types is very useful, even down at the level of models of computation, like the typed lambda calculus, as opposed to the just baseline lambda calculus, these very low-level models of what computation is. So it's a really useful idea and abstraction, and one of the points of this talk is to bring some of these ideas about types into neural networks. So the fundamental purpose of types is to give meaning to binary values. So this binary string that I've got there, 11001001, etc., could be interpreted as two different things. It could be interpreted as a bitmap, in which case you get the image in the bottom left corner of the slide, or it could be interpreted as a real number, a binary sequence that corresponds to a particular real number. And in that case, it would be interpreted as pi. This is the binary expansion of pi. And once we have types, we can convert in between types. So maybe at one point, I need to, say, communicate this number pi through a QR code type mechanism. And then this image representation of pi would be really useful. Or maybe I want to compress it, try compressing it, and I want to use, say, an image compression algorithm to do it. So being able to convert it to a different type gives me access to a whole bunch of different algorithms. Algorithms that are not available for working with just binary sequences that are real numbers. And new types can just in general make your life easier. So for floats, multiplying is easy, but adding is hard, because fundamentally floats are like a logarithmic representation of numbers. Whereas for binary numbers, just binary sequences to represent our numbers, multiplying becomes kind of hard, but adding is really, really easy. Adding just basically becomes the XOR operation. It's like not even just a single line of Python, it's like a single CPU instruction, which is amazingly simple. So just switching to a different type can sometimes take a problem that was really difficult and turn it into a problem that is really easy. So for example, if you're manipulating a directory by its name, if that name is a string, then there are lots of problems that can be kind of difficult to solve unless you convert it to a path first. So the path object available in Python's pathlib is like a representation. It's basically you put in a string and you get out a structured representation in which you can easily make the manipulations that you need to make with directories. It's much harder to treat it the way you would normally treat a string. Like it's harder to say, make it all uppercase, but you don't need to do that with a path. You need to do things like get rid of the directory or append a file extension, something like that. So I'm going to work through an example of this to make sort of really clear just how important it can be to think in terms of different types. And so the example is going to be based off of a failed Python enhancement proposal, PEP 313, which was an April Fool's suggestion to add Roman numeral literals to Python. So, unfortunately, this PEP was rejected and not added to Python. And so there are no Roman numeral literals in Python. So if we want Roman numerals, we're going to need to roll our own. So what we want to be able to do, at least, to just get started with this Roman numerals type, is we would want to take the built-in integer type in Python, which can handle Arabic numerals, so the numerals that folks who write their numbers in English are very familiar with. And we want to take those kinds of integers and turn them into Roman numerals. Now, a fun fact about Roman numerals is actually they stop at 3,999. The Romans did not need to count things as big as we need to count in the year MMXX, the year 2020. But so we only need to focus on these numbers, but even just in this smaller set of numbers that the Roman numerals properly cover, there's actually some interesting stuff going on. So it starts off looking like a tally system. 1 is a single I, 2 is 2 I's, 3 is 3 I's, but then 4 comes out of nowhere with an IV. And then 5 is a V. After that, 6 is a VI. Then, these more complicated patterns start to arise, and by the time we get to 3,999, the mapping between the number in Arabic and the Roman numeral representation is not so simple. So we go from those 4 numbers, 399, to MMCMXCIX. And so just looking at this problem as a single step, as a type conversion from Arabic to Roman numerals, this looks pretty challenging. But there's this actually great blog post by Sandy Metz, who is a Ruby programmer, who described an insight that actually there used to be several kinds of Roman numerals, and one of them is what she calls additive Roman numerals. And so converting the additive Roman numerals are actually really, really simple. So the Roman numeral for 4 or the additive Roman numeral for 4 is just I. It's 4 I's. And then the additive Roman numeral for 9 is VIII. And so it's much simpler to convert from Arabic to these additive Roman numerals than to convert from Arabic to the Roman numerals, the ones everybody knows about, which she calls subtractive Roman numerals, because they've got this special thing where sometimes you subtract one of the values. I from V gives you 4 in normal Roman numerals. And so it's really easy actually to translate from additive Roman numerals to Roman numerals. It's very straightforward to just replace those specific patterns with this subtraction. And so her insight was actually, converting from Arabic to Roman is one idea, but that should actually be sort of split up into 2 pieces. Arabic is much closer to additive Roman numerals than it is to Roman numerals, so let's do that step first, rather than sort of conflating these ideas into 2 steps. So I actually had read this blog post a while ago, tracked it back down for the purposes of this talk, and decided to implement it myself. And in the end, it turned out to be actually just as easy as advertised. I needed to, do a little bit of chin scratching, but in the end, I got this really, really simple, 20-something lines of Python to convert Roman numerals from their integer representations. And just as she said, it was so much easier once I thought of it as a multi-step process with multiple types in it. Not just Arabic numerals and Roman numerals, but also this new additive Roman numeral type. And I even added an additional type in there, a semi-additive string, to make it even simpler and turn it into basically just some 3 steps, essentially. First to this additive type, then to a semi-additive type, then finally to this subtractive Roman numeral type, using only the sort of very most basic of Python operations. So new types can just make your life a lot easier. We already saw that the additive Roman is much easier to translate into the full Roman numerals, but it's also true that addition and multiplication are actually kind of easier in additive Roman. So to implement addition on Roman numerals, what you actually probably want to do is convert them to this additive Roman format, then implement addition there, and then maybe transmit it back to Roman numerals. So the addition of this type gives us, not only does it make our initial problem easier, but it actually makes a whole bunch of other things we might want to do with Roman numerals easier, because we've got this nice nice representation, this alternate representation in a different type. And so what this means is, like, this additive Roman type becomes kind of like a hub if we want to switch between things. So if we want to switch over to like a Babylonian number system, which is sexagesimal, meaning it is base 60, it's where our time system comes from. If we want to switch over to that, additive Roman, easier to switch over to Babylonian than from Roman. Similarly, if we wanted to switch over to pure tally marks, it's extremely trivial to switch over to tally marks from additive Roman, but much harder in regular Roman. So if we make something that can convert between these types, then we actually give ourselves essentially like an exponential increase in the number of things that we can do just by doing type conversions. The issue with this is that new types are actually kind of hard to find. So we were able to make this additive Roman type, and actually, I think in Sandy's description, she found it in the Wikipedia page describing the different versions of Roman numerals that are around there. But the types that we can make are actually pretty limited, as always when we're doing traditional computing with programming in Python rather than machine learning, by our capacity to reason. We have to reason our way to a type. We have to say, okay, here's the way this binary representation is used. Let's turn it into a different binary representation and use it in this different in a different way. And we have to think through that explicitly. And wouldn't it be great if we could actually just sort of like discover the types that we need, right? If we could automate the process of finding the types that we need for our computer programs, that would be really, really great. And the problem, I guess, for traditional machine learning is that linear models cannot discover new types. So if I do a linear prediction on data, so let's imagine a classic example of predicting whether something is a picture of a cat or a dog. If I do a linear prediction on that data, all that happens is the data comes in, I do one operation on it, and actually after that linear operation, I'm basically done. People include a softmax. That's not really strictly necessary to get out your prediction. Really, once you've done the linear model, once you've done that linear transformation of taking the weights and dot producting them with the data, you're basically just you're done. That's it. So there's none of that ability to sort of like say, oh, what if this data were a different type? Maybe my prediction problem would be easier. Whereas neural networks can actually discover new types. And so if I think about what my neural network is doing, it's applying a couple of different transformations in sequence. Right here, I've basically only done one, but one could do it for like a much deeper network. And then at the very end, once I'm just before I'm ready to make my prediction, I actually apply that linear predict function, right? I take some weights, I multiply them by the activations of the previous layer, and then I pass it through a softmax, and that gives me my prediction. So the final layer, actually, the top of the neural network, is this linear prediction step. And so you could think of it as actually what's going on is that every other part of the neural network is doing a type conversion from data, the type data, which here is images, to the type embedding or embeddings of images. And those embeddings are going to be some complicated, high dimensional representation. They're hard to understand what's going on in an embedding. But what the property that they have is that it's really easy to use them to do the downstream prediction tasks, sort of by design. So this is typically called an embedding, right? So this view that what we're doing is creating a new type. The result of that type is typically called an embedding, and the intuition there is that our data sitting in its natural form, in its natural like binary format, or in its natural matrix format, is in this like tangled up state where maybe like pictures of some foxes and dogs are very close to pictures of some cats because they share colors, and then other pictures of things that are very much like dogs are very far away from dogs, and so it can be very difficult to, with a simple model, split out our dogs from our cats or solve in general our task. And so what happens instead is that in the course of that neural network's application of transformations to data, it produces an alternative coordinate space, an alternative representation of the data, such that all the dogs are on, say, the left-hand side, and all the cats are on the right-hand side, and things that are kind of ambiguous right there, which we're not sure whether this, pangolin is a dog or a cat. That's not one of our possible responses is not pangolin. And so it sort of ends up right here in the middle. And so this intuition that it's embedding comes from like the world of topology, comes from physics, the idea of like taking a collection of points and then putting them in a different shape in a different space. So it's an intuition that doesn't bring ideas from computer science so much as it does bring ideas from applied math. One of the consequences of this perspective is that we should think of neural networks as being cut kind of differently. The traditional way of representing a neural network, and this is from a Condé Nast /tech article, is to think of them as an input layer, then hidden layers, then an output layer. And that emphasizes this like split between things that are visible and things that are invisible, sort of things that are on the interior and things that are on the exterior. But this is, I think, not the right way to split them up. The way we should sort of split them up is actually, so 4 parts. So rather than tripartite, a tetrapartite partition of our neural networks, where we have data and predictions on the ends there. We can still keep those. But then we split basically between that final linearly separable embedding, that embedding that is really useful for a linear model. And then we split that off from basically everything else, which is the sort of internal representations of this model, which need not necessarily be a useful embedding for any, linear model. So we should focus on that embedding part there. And actually, this connects to some ways of thinking about neural networks that are popular in the sort of traditional stats community. So this is 2 tweets from Daniela Witten, who was at one point the MC of this Women in Statistics and Data Science Twitter account, which every week features a different woman in data science. And so during her week, she made sure to basically kind of troll the internet as much as possible. And one thing she did was point out how many things are just linear models, where you're trying to guess something, and you're trying to make a model that guesses an output, and she'll say whether it's just a linear model or not. And her answer for deep learning was kind of interesting. She said, as a function of the nonlinear activations, it's just a linear model. That is, like, once you only think about that last layer there, basically everything we think about neural networks is pulled from linear models, whether things like SGD and regularization. Like we draw those ideas from the world of linear modeling, and what we've changed is just the representation that goes into the linear model. We've changed the type of data that the linear model operates on, and that's actually a much smaller change than you would think. For how impressive the behavior and performance of neural networks are. I think it sort of suggests how useful a good linear model can be once it's fed good data. Though the one important difference I want to point out is that the intermediate layers of a neural network are also typecasting functions. So it's almost as though if we wanted to convert from a float 32 to, say, a float 16, so from single precision floats to half precision floats, on our way to doing that, we also spun off, oh, this is what it would look like as a 24-bit float. And this isn't the way our normal sort of typecasting functions behave, right? Normally, we would just go straight from float 32 to float 16. But neural networks are not like that. Neural networks actually produce effectively a series of embeddings that get progressively more useful to a linear model. So the way that I actually like to think about it is that a neural network is a composable typecaster. It's self-composed of composable typecasters. So each chunk of your neural network, as you slice off each layer, is a different casting to a different type. And you can compose these together to get a casting into the destination type, this linearly separable data at the end. So I think it's important to take a moment to explicitly state why I think this perspective is useful. I think the biggest thing is that it makes it more clear how to compose neural networks, right? So one of the advantages of neural networks, if you hear people talk about like, okay, why are neural networks so good? And why did the people who worked on neural networks back in the like late 90s to early 2000s, when they weren't that impressive in terms of their practical performance, why did they think neural networks were what it was? Why did they think that this was the important technology? And the answer, like almost all of them give, is that neural networks are composable. I can take little modules and combine them together. But if you look at the way we write neural networks, we often write them such that the output is this final prediction, right? The output of the network is, just dog, or like a one hot vector that is the dog, or like the softmax of the logits, whatever it is. And that's actually not something you'd want to put into another neural network, right? You wouldn't actually really want to take that output, that softmax output directly and put it into another neural network, right? That's basically just a distribution over your classes, and that's not always the really useful thing. The thing that's actually much more useful and actually makes a good input to a downstream neural network is that layer before the linear transformation, the softmax, that embedding, or even just like concatenate together several layers and turn that into, say, like a multi-channel image that represents the input to the neural network. That is a really good input to a downstream neural network. So this allows us to compose, to combine in a chain multiple neural networks. It also encourages you to de-emphasize supervised learning, right? If the goal of training a neural network is to get this embedding here at the end, rather than directly to solve the task, then the task is actually less important. The important part of what the task, I think, really brings us is that it tries to encourage a rich, useful embedding representation. So it encourages you to instead think about unsupervised learning, or as I have it here, fun supervised learning, which is, in addition to probably generating better embeddings, is also less expensive, right? If I want to do supervised learning on every image posted on the internet, not only do I need to download every image posted on the internet, I need to get humans to label every single image posted on the internet. And humans have written a bunch of stuff around images on the internet, but they haven't done it in a way that's quite useful enough to be, or that's quite the right format to be useful for supervised learning. But if I do something like an autoencoder, so an unsupervised learning task on images where the goal is to take an image in and return it at the end, then that I don't actually need those labels anymore. And so I remove actually what's the most expensive and difficult step in my supervised learning pipeline. So by focusing on generating good embeddings, you actually, I think, recognize that there are better ways to get the downstream final thing that you need, right? When it comes time to do the downstream supervised task, you could take those embeddings that you learned in an easier, cheaper, more scalable, unsupervised manner, and then fine tune them to get that final supervised task solved. And in that case, you're just training a linear model, and all the tools and ideas from linear models and statistics come in handy. This perspective also pushes you towards this model amalgamation style. So this is a sort of graph of a fake machine learning pipeline that takes in raw data and then generates three different things: a prediction of, let's say this is a social network, who might be friends with a user. So this is raw data about a user, maybe what they've been clicking on, like their email and information about them. And it produces first a user embedding and then a prediction of who they are friends with, and also a recommendation of maybe other people they could be friends with or other content on this social media network that they might like to see. It also predicts what they're going to click next. Maybe that might be helpful for your content delivery network to come up with smarter things to cache. But all of them pass through, rather than going straight from raw user data to click prediction or straight from raw data to friend prediction, they pass through this central node here of the user embedding. And this is behaving kind of like that additive Roman type that we had before, right? It's a useful intermediate type on which the operations we really want to do are easier. And so all of these arrows here are actually DNNs. But the difference is that sort of the most important DNN in the entire pipeline is this first one here that generates from the raw data a user embedding. And that neural network is the most important one. And that's the one, that's best understood as just a typecasting network. And in fact, all of these this click prediction, recommendation, and friend prediction, these could even just be linear models on the user embedding if it's good enough. And actually, this is not just a sort of toy example. Or at least it's not just for tour examples. So I've talked with folks at Google and folks at Twitter, and this is actually what they do. They may have like 150 models in production, but actually the core of it is an embedding model that then gets a model that produces these embeddings that gets fed to everything else. It also raises some important questions for the future of ML-powered technology. So just like three kind of research almost questions or broad scale questions that come up out of this. The first is sort of, how can we document our types? An IEEE of NN learned types would actually be really great. So IEEE is the ones who put out that floating point standard, and they define, how you're supposed to behave on a bunch of like if you implement floating point, like what does that mean? Like how does that constrict the behavior of your type? And IEEE standard for say embeddings of images, embeddings of natural languages, all like there's lots of data types out there that get used all the time in machine learning, and having a centralized standard would both level the ML playing field and make it easier to develop ML applications without having Google scale resources. And it would actually centralize some of the really hard work that's out there, like removing bias, extremely difficult to do on your own. The techniques are very sort of like experimental, and there's not a clear choice. There's not a cookbook. But if we had a centralized repository for doing this, then we could come to a consensus on what an unbiased embedding of an image is, and that would be extremely useful. Also, things like compression to get high performance. This is non-trivial. Putting this all in one place, we could end up with a neural network that does that first embedding step and does it in a millisecond instead of a second. And so I think that, adopting an approach in which we have defined types that are, NN embedding image, available in the Python standard library could be really useful for machine learning. Also, on a more research level, there are a bunch of ideas in algebraic data types. So like once you have types, you can actually, there's like a mathematics of working with types. So there are sum types, product types, exponential types. There's also been some exotic ideas in, I think, the last 10 years or so of calculus on data types to generate things like lists arise from applying Taylor expansion to expressions in the algebra of data types. And I think that there might be some low-hanging fruit out there for ways that we can combine the results of neural networks in a smart way or extend them. And then lastly, now that if we really think that what's going on here is that the neural networks are learning a smart embedding, maybe neural networks aren't the right choice. It hurts me to say this as a big fan of neural networks and somebody who's kind of all in on them. But maybe there's actually better ways to learn types, right? The fundamental goal here in machine learning is to learn programs, is to learn computer programs that take inputs and produce the appropriate outputs. And if we actually take a, sort of more typed approach to this, and we realize that what we're really trying to do most of the time is learning types that make our programs trivial to implement, that really changes what we think are the most important sort of research directions to pursue. So there's a nice little blog post there that indicates what that calculus of data types, where that arises from. So this is just a sort of perspective I've come from, like sort of combining together a couple of different ideas that are out there in the world of ML that you may have come across, and trying to take this idea that the embeddings of a neural network are actually more useful than the outputs, and trying to give it a bit of a more computer science flavor, and to think of these embeddings actually as types. And I think this has actually helped me interpret a lot of the things I've learned in the sort of recent salons that we've had, and in recent papers that I've read, and hopefully you'll find this useful as well. All right, so if there's any questions, if anybody has any questions they want to ask, I'll stick around for a little bit to answer them. If not, we are a little bit over our time, and so I'll just end it.
Charles, that was a great talk. I have one comment. I guess I'm curious about, there's probably an analog here between like neural networks that are explicitly designed to be compositional or modular. So I'm thinking of kind of modular neural network architectures that, for example, Jacob Andreas has worked on, where you explicitly have different neural modules which you can piece together in various ways. And the output of one neural module, for example, is like some sort of embedding that's useful for identifying the color of an object in an image, some sort of embedding that's useful for identifying the count, the number of objects in an image, right? And so there probably are some tie-ins between the kinds of explicit types you've mentioned here and these neural network architectures that specialize for producing certain outputs of specific types.
Yeah, that's actually a good point. I think one thing that is suggested by this is that maybe actually you want those intermediate types to also be, say, useful for linearly predicting features, like you mentioned, the color of an image or something like that. Or like it could also aid with like problems of explainability and interpretability if you have submodules of the network that are explicitly dedicated by means of like they must produce an embedding that's useful for a particular task to, say, shape inference or texture inference or like being useful downstream for segmentation or not being useful for segmentation. You could also explicitly say, do not be useful for this particular downstream task. I think, yeah, you could enrich these intermediate embeddings that the neural networks are producing and make them uh, make them more powerful, make them more useful, and make them more modular. So I think it's an idea a lot of people are kind of circling around, and I'm excited to see where it goes.